Okay, so
As I mentioned a minute ago, what we're going to do is go through a few things today. Towards the end of the hour, I suspect I'll be talking for a half hour, 45 minutes, something like that. Then the last half hour to 45 minutes, maybe an hour of class, I'll get back around to help everyone finish up their code. To be quite honest, I'm not going to touch it today, so as long as I have your code submitted by tomorrow morning, you're good to go. I'll be looking at grading it tomorrow morning. It's very important that you get the CCD algorithm nailed down because we're going to be using the same program in our next programming lesson in developing our trajectory. Okay, we're going to focus, as the last point suggests, specifically on, I suppose I need to turn on the microphone. We're going to be focusing, that's too much, specifically on linear interpolation. There's a number of different ways that we can develop this trajectory, but we're going to be focusing only on the linear interpolation, which is nothing more than drawing a line between our origin destination and making the end effector follow that line. We don't care about what any of the other joints are doing. The only thing we're interested in is making sure that end effector follows the path that is attached to the line. So we're going to quickly talk about the last two assignments. After we do that, I'm going to talk about the speed of the CCD algorithm, because probably a few of you have looked at this and said, there's no way we're going to select a destination, perform this CCD algorithm, and then move to that destination. That's probably not going to happen, because the algorithm we developed, if it takes 45 seconds to determine the solution, that's just not feasible. We can't be, selecting a destination, waiting 45 seconds, and then moving to that destination, right? So we'll take a look at that real quick. I'm going to quickly introduce dynamics, which really means I'm basically just going to touch the surface. Ultimately, I hope I can give you just enough information on the dynamics. Frankly, the dynamics are a course in itself. What we really want to do when we start discussing dynamics is get to the point where we can discuss the forces associated with motions on that manipulator, so that we can start sizing the motors for each of the joints. Because we need to be able to hold that manipulator in a fixed orientation, meaning that we have to consider the holding torque of each of the motors on each of the joints, and then we need to be able to move it as well. So we need to be able to have a dynamic torque associated with the motor as well. As I've already mentioned, generally we're going to be looking specifically at stepper motors anytime we're building a robot. Stepper motors are very interesting in that they have a step response. Essentially what you're doing when you're sending an address to a stepper motor is you're telling that stepper motor which one of 4 increments you're wanting to move to. Okay. For that reason, there are typically 4 lines on a, well, I should rephrase that. On a basic stepper motor, there are usually 4 lines. Okay. Those 4 lines represent 2 separate coils within that stepper motor. Those 2 coils can either be have a north-south pole or a south-north pole. And for that reason, what you can do is, if you have a magnet on the armature of that motor, you can specify the location of that armature based on the polarity of those 2 inductors, or those 2 coils. If it's north-north, then you might be having that armature pointing due north. And then when you migrate to a north-south configuration, you might be sitting at a 135-degree angle, and so on and so forth. Now the thing is that we know that the step resolution is typically 1.8 degrees on these stepper motors. And for that reason, what they do is they actually put teeth on that armature that provide the preferred resolution that we want. So now you have a tooth that just happens to be aligned with one of the four possible angles, and that's what gives us our actual step resolution. We're not going to concern ourselves a great deal with that. The key thing on a stepper motor is just know that the position is addressable, okay? You can very accurately track the angular displacement that you move through just by counting the number of 1.8 degree steps that you've sent to that stepper motor. And there's an inherent problem with them. If you overload that stepper motor, then you're going to skip a step. And in fact, you don't skip just one step, you skip 4. Because if you send the pulses out of sequence, you're going to skip the next 4 subsequent steps, meaning that you're going to be, what is that, 5 times 1.8, so 9 degrees out of phase with where you should be, okay? So there's those issues. But in general, we use stepper motors because we can very accurately keep track of position. What other way could we move these motors without the use of a stepper motor? And how many of you took the 277 class, the Intro to Robotics? Okay, so they didn't use stepper motors there, did they? They used servo motors.
Yeah, we use servo for the
Okay.
production box.
So what's the difference between a servo motor and a stepper motor?
But servo kind of still, it has like a gear in there still.
Okay.
It goes by like, degrees. We kind of, I don't know, it was kind of weird. You just put it into the computer and you did like how many degrees you wanted it to do, and it would do it kind of like a potentiometer.
That's exactly what it is. So what a servo motor is it's just a straight DC motor with a feedback loop built into the electronics, okay? And what happens is when you are moving that motor, that DC motor is attached to a small gearbox, and inside that gearbox you have a potentiometer, which is just a variable resistor, and when you want to move to a position, you set the reference voltage on the sense line, and the stepper or the motor is going to turn the shaft on that gearbox until the sense line, the sense voltage is the same as the measured voltage on your potentiometer. So, which do you think is more accurate? Well, I should never use that because, of course, it depends on how much money you're willing to spend, right? Okay. Because you can buy $10,000 servo motors that are incredibly accurate. But on the other hand, you can buy $10,000 stepper motors that are incredibly accurate. The real thing is, I mean, if you think about the mechanism involved in it, what you have to recognize is that because a typical servo motor has that potentiometer, it's going to be inherently inclined to fail eventually. It's going to have a lifetime. And if any of you are into model airplanes, using those little servo motors for the different axis of control, you know that eventually you have to replace them because they're just not a high dollar item. Okay? More expensive and more reliable servo motors actually use optical encoding. So what they have is a diffraction grating that as you rotate, it just counts the number of steps by transitioning light and dark. So essentially it has a, I guess I better run it the screen here. And I can clear this one. Okay, so how many of you have ever taken apart a printer? Printers are amazing at doing this. So if we want to be able to determine the position of the motor, what we can do is on the shaft of the motor, we can just put a wheel on it with something that we can count. Okay, let's say that we have a little photo transmitter here, and we are facing that photo transmitter so that the transmitter is on this side, the receiver is on the back side of that wheel. And as we're rotating it around, we're going to see a black region here representing a 0, a bright region here representing a 1, 0, 1. So if we have, say, 16 slots in this, all we have to do is count 16, and every time we see 16 pop up, we know we completed one full revolution. That's one of the easier ways that these printer manufacturers have gone to in order to save them from having to buy stepper motors. So what they do is they use just a regular old DC motor. They encode it with one of these encoding wheels and essentially turn it into a servo motor. Okay? This is much more reliable than a typical potentiometer-driven servo motor because light doesn't involve a bunch of friction, right? I mean, you don't have to worry about light wearing out. Okay? So with that being said then, we can employ the same idea in high dollar servo motors just by placing an encoding wheel. The resolution of the encoding wheel is going to determine the resolution of the servo motor, and with that then we can significantly improve the reliability of that servo motor. So, yeah. So as an alternative, you can go to servo motors. What can you probably say about servo motor though? So when you move aileron, or are the aileron the horizontal ones, or yeah, they're the horizontal. Okay, so when you move an aileron with a servo motor, what's actually holding that aileron in place?
So like the gear of the servo motor? Just
Yeah,
to hold it
it's
in.
the gear. It's the
Like with the robots, if you like picked it up, sometimes it would just start going back down. Or something.
that's exactly it. So in that case, the only thing holding that position is the gearbox itself. Okay, so in the case of the servo motor, if you want to hold a position, what you have to do is apply a counter EMF in order to maintain that position. That's kind of a problem, isn't it? Because if you apply a current to a motor, specifically a DC motor, it's going to expect to turn. If it's not turning, then you're going to end up burning something up. Okay? A stepper motor, you don't have that issue. You can apply what's known as a holding torque to a stepper motor without ever having to worry about burning up the stepper motor. So that's a huge advantage of a stepper motor over a servo motor as well. Okay, so with that being said, wow, that was easy to get off task. Let's talk about the last two assignments. Okay, so because we only have 2 weeks left, we don't have time to have 2 subsequent programming assignments. So I was toying around with how we could structure the last 2 assignments in order to still make them kind of useful. And what I think I'm going to do after I review these videos, make sure that they're not designed for 2-year-olds, is have you guys watch these videos. They're about 45 minutes each, and then provide even 3 to 5 paragraphs is probably a bit more than I care to read, but a response associated with this. Now, after I review them, I'm going to direct that response a little more completely. I'm going to say, okay, provide a brief response relating to the kinematics of the robot that they discuss, or whatever the case might be. But it'll just be a way, it'll be that sixth assignment that I promised on the syllabus, so that you don't have an overweighted, grade based on 5 grades instead. It'll get that fifth or sixth assignment in there, but it won't require a bunch of extra time in order to do the programming that we would need for the subsequent programming activity. The other assignment is our final programming assignment in here, and it will be applying the linear interpolation algorithm that we'll introduce hopefully later on today or first thing tomorrow into the code. What this is going to do, as I've already mentioned, is it's going to go through and select a starting point for the end effector, a destination of that end effector, and then go through and calculate the series of motions necessary in order to follow a straight line. So it's going to be using that CCD algorithm over and over again, okay? What's going to happen is if we have, I keep on doing this. Okay, so if we have a starting location, a destination, what we're going to want to do is follow the straight line path between those 2 points, okay? This is exactly what's going on with a CNC or with a robot over there when we move from point to point. It's following a linearly interpolated path. What we're going to do is go through and break this line up into a bunch of intermediary steps. And then what do you think we're going to do? We're going to calculate the cyclic coordinate descent algorithm to achieve this point, do it again for this point, over and over again. What do you suppose the only challenging part of this really is?
Telling it when to stop.
Well, telling it when to stop. Actually, we can say stop when we reach the destination, right? If we know where we're starting at, where we're dividing.
Wouldn't it be to make sure it goes to each point in the correct order?
Yeah, we're going to make sure it's going to each point in the correct order. The most difficult part of this is figuring out how to represent the line that the manipulator is following. And this just goes back to our algebra. We know that, what is it, y2 minus y1 is equal to m times x2 minus x1. And from that, we can say that y2 minus y1 is equal to y2 minus y1 over x2 minus x1 times x2 minus x1. Okay, that seems really redundant and unnecessary. But what we're going to do is go back to the general form of a line. And with this general form of line, we're going to figure out what the line equation is for this, and then just pick 10 or 20 or 50 or 200 points on that line that are sequential, moving from the starting point to the destination, and apply our CCD algorithm to each of those. Okay? So it's a really nice, easy way to go through. For those of you that are in EET477, I think in chapter 7, they talk about interpolation. It's the exact same interpolation algorithm, you're just going through and picking 2 points and figuring out an interior point. Anytime you're interpolating, that's what you're doing, is picking an interior point, assuming 2 boundary points, okay? So it's going to be really straightforward when we get there, as long as your CCD algorithm is working. So make sure that you get it running well. Okay, so is everyone good with the 6th assignment? Trust me, I'm not a big fan of report writing either, but since we just simply don't have time to do 2 programming assignments, I figured this was a viable alternative. Do you guys agree with that? Okay, there's not going to be a rubric, it's just going to have to be moderately intelligent. You know. So, okay. So with that then, let's go in and talk about the speed of our algorithm. And I should have had met that one already. This is going to adversely affect my speed. Okay, so I have a script here that is exactly what I did for problem number 1, except for I removed some of the, I removed the outside loop so it only runs 1 time, and removed a few of the other things. I introduced a timer in the script, so it is, there we go. Okay. So this is exactly what I put together for my solution. Except for I didn't update the notes. I hope this is the right one. Let's see. Okay, so Aaron. So ideally, yours should look something like that, but yes, okay. You'll notice that I have introduced a timer in this somewhere. So let me find it here. What I did was I said, okay, I want to record the time right after we click the destination. That way I know when we started. And at the bottom, I'm going to calculate the elapsed time. And this is kind of cheesy, but it'll work. By taking the current clock minus the time we started. Okay, so I could do a lot of formatting to this, but that's okay. So in this case, what we see is that we have 1 minute and negative 53 seconds. Okay, that's kind of lame. That's 7 seconds, right? Or right around 7 seconds. That means that in order to generate this solution, it took us about 7 seconds in order to do so. Okay, wait for it. It's reaching, it's reaching, it's reaching. Good, so in this case, we've got about 14.5 seconds to generate that solution. What's the number one thing slowing us down here?
When it's pointed directly at the destination, like it doesn't, we don't like intelligently adjust the correct drawing. It always just sits there and kind of.
Right, I mean, and that's the thing with this algorithm is it doesn't use an intelligent approach, it uses a predefined approach. This is exactly what I try to do with my 221 guys. I don't try to introduce anything intelligent, I just try to introduce a procedure to analyze the different circuits that we run into. I'm sure you guys remember that for those of you that had me for 221. That's why we time and again fell back on the 4 and 5 step processes, because I knew that half the class anyhow was MET students. It's one of those things where since we have such a wide variety of people in that class, you know, some of the people are just taking the class to get through it, right? And for that reason, it's not practical to go through and fully teach all the theory behind it. That's where EET477 and 324 come into play. Okay, but anytime you're introducing an algorithm like this, you have to realize that that algorithm is only as good as the process that it uses. In this case, there are many other ways we could implement this, including adjusting the base joint if we're reaching a long ways away. But this algorithm uses the same approach every time it runs, okay? But my question is not necessarily, you know, how we could improve the algorithm, but what is providing the significant, the most significant part of our time in calculating this.
Well, we're carrying around recalculating that matrix, I mean, doing all those operations every single step, I guess.
Okay, but the thing is the computer is running at 2.6 gigahertz, right? So it doesn't seem like, you know, these calculations should really slow us down a whole lot. The monitor, on the other hand, is cruising along at, well, 30 to 60 hertz. So the monitor is only refreshing. If you have a good video card and stuff, it's refreshing about 60 times a second, and that's what's going to really be slowing down this calculation, okay? So a significant portion of this 14.5 seconds is associated just with drawing your solutions, okay? So let's go through and get rid of all the stuff that involves drawing the solutions. What I have done here, maybe that's not it. So open, okay, which one is it? Ah, here we go. Okay, so what I have done here, you'll notice that if we switch between here a few times, scroll up to the top. Okay, first thing I did was I did not define my initial DH parameters. Okay, those are already stored in memory. So in order to get this to work properly, I have to run this script first so that it loads the initial DH parameters into memory, and then I can run the second one. The reason I did that is I didn't want the code generating a new set of DH parameters. I wanted to be able to truly compare the time it took to generate this solution to the time it takes to generate the same solution without the graphics. Okay. So in this case, I made sure not to define the DH parameters because they're hopefully already stored in memory. Okay, and I did not go through and accept a mouse click. Again, the X test and Y test are already stored in memory. Okay, so if we go back to here and run this, we go through and wiggle along until we get the destination. And when we get the destination, it says it took 8.7 seconds. Okay, so that's not too bad. I mean, I suppose that wouldn't be a bad thing to make somebody wait 8.7 seconds to move a robot. Okay. But if we remove all the stuff in the middle and stop clicking wildly here, we'll run this guy. Oh, well, that was quick. So, took 0.24 seconds. So without doing all of that intermittent drawing, what did we save ourselves? It was 8.7 seconds? Yeah, so we're looking at almost an entire, well, over a magnitude of difference. I mean, this is, what, 50 times faster about? Because 10 times faster would be 2.4 seconds, and then, so I guess it's 40 times faster. So by not going through and providing all of the intermittent steps, we see that we're arriving at the answer in 1/40th of the time approximately, okay? So, and it doesn't really matter how complex a solution is. Okay, let's go through and find one of those border solutions that I'm sure you guys absolutely hate. So this is the original one. So I'll reach clear up here because that's bound to take a while too. Maybe not. Well, that was surprisingly not that bad. So let's see how long it took. So 9.3 seconds, that thing sucks. I've had some that have taken like 2 and 3 minutes to run, so I'll run this again. And let's say we're, I don't know, just do it. Okay, this is taking a while. So they're thinking about it. I'm running a bit short on time, so I'm talking a little bit too much. So what I'll do is, after I get done with this, I'll just cut it off at that point and come in tomorrow and provide my little introduction to the dynamics. That way I can give you guys the rest of the hour to help you out on finishing up, so. Okay, so it's still running here, and what you run into, as I'm sure many of you found, is that as soon as you start approaching the boundary of your workspace, the solutions tend to take longer and longer to generate. And the reason for that is because it's pretty hard to adjust those joints without having a fairly insignificant overall effect on the distance to that destination, okay? In fact, this would be a good situation where you do something like if you run through 50 times without achieving a solution, or 100 times or whatever, without achieving a solution, then you make a major adjustment on the base joint in order to, force it to calculate a new solution, okay? But we'll sit here and just let this spin its wheels, because obviously it's taking a while. Anyone do anything exciting? Go outside at all yesterday?
I went to the Richard Sherman softball tournament.
Oh, how was that?
Every celebrity that was there was drunk.
Oh, wow.
Oh, yeah, they were like holding drinks in their hands.
Was that here in town?
That was in Seattle.
Oh,
It was like 22,000 people at the stadium.
Cool.
It was pretty cool.
Yeah, we had about 40-mile-an-hour winds here yesterday, so I had this idea that I'd go out and mow the yard, and then when I saw the dogs weren't, standing up, I decided not to. Seriously, the wind was horrible yesterday.
I tried to go running yesterday and
Yeah, that doesn't even sound like a good idea. I'm going to try a different solution here. So I'll break out of this one and come up with another one that Okay, so try running that again. And maybe something not quite as challenging. The entire point of this again is to determine how long it takes in these more challenging situations to calculate all of these inverse parameters without graphing the intermediary steps. Almost there.
What's that painting? Michelangelo, like Scott did that. This thing here, it's not gonna happen, just almost there. How much we get to know that painting?
Did you guys watch the Ninja Warrior gal that ran through the course in like record time, actually completed it?
Oh, the,
I just saw that she did, but didn't watch it.
Yeah. Doesn't look like a super challenging course. Of course, I say that
Yeah.
because I've never done it. But you can definitely see why people have a hard time with it, so.
I like to make fun of the people on the TV with the beer and popcorn.
Yeah.
in hand.
You see these guys that are, you know, just built like a rock and they go up and don't make it through the first part.
Yeah, in that sort of situation, it doesn't pay to be like heavy at all.
Yeah.
No, the skinny guys always do better, the scrawny ones, because it's like, for the first one it might be okay, but, you know,
The problem is like they do the jumping thing, they have to be
Move that vertical.
those like, when they were comparing the different athletes, they get the professionals of like each different sport, and like, the gymnasts generally do pretty good, the track guys do alright until like the second or third round.
And then they get like the random guy who's like a priest or something. He's like, oh, this is my hobby. And then he makes it through the
It was
whole
like
day.
the Japanese version, the first person to complete it was like a fisherman or a firefighter or something.
Yeah.
It's like,
And then they had like one where it was like an open thing, so like anybody could come up and like try. And this guy like
10 minutes.
nailed it. And it was just, I felt so like, I could stress through the whole thing like the whole time. I've watched it.
Yeah, so right now you can see that the first link is sitting down here, so I'm really close to the boundary of this, and it's just taking a while.
I was gonna ask, how did you get it so that your final one each time when you run it, the red is above all the cyan and stuff? Because mine always goes underneath it.
What I did was I just did a final plot outside of my loop
Okay.
and forced it to draw it, you know,
Okay.
one final time outside. So kind of a cheesy approach, but
It works. Mine was driving me nuts because it keeps going underneath all the teal.
okay. So let's do this. So in this case, we're sitting here running along. We haven't got a solution yet, and it's been quite a while, so I'm just going to break out of this. Let's see. I'm going to jump over here and do the exact same thing, separate without the intermittent drawings, or intermittent path generation. So, sitting here, spinning its wheels. More than likely, this is partially a result of the step resolution too, so let me fix that. So in this case, now that we're not drawing all the intermediary stuff, I can really crank in the step resolution. And what this does is it requires a significantly more calculations, but since we're not graphing the solution, then it's fine because we're not having to go through and redraw the solution each and every time. Report. Oh, it's because I've decided to freeze on. Okay, so. This again goes back to the memory hole that I was telling you about. When you break out of the loop too many times, it starts to, it doesn't, for whatever reason, it doesn't go through and purge the memory right. So you end up with a bunch of unused memory, and then you have to swap around that memory, and just generally is not a good thing. Okay, so let's try this again. Okay, so I will go in, and that's got an angle resolution of 4 there. I'll leave this as an angle resolution of, well, I'll just leave that as 1, just to demonstrate that even with the increased angle resolution, it still is quicker. So this has an initial angle resolution of 4 units, and then as it approaches, it changes to 1 degree per step. And with that, then we see that the total elapsed time was 11.75 seconds. Jumping over here, doing the same thing, we have an elapsed time of 0.89. So again, significantly faster by not redrawing those intermediary steps. This is where the linear interpolation is going to come into play. We're not going to try to draw the solution progress between each steps. All we're going to do is use the CCD algorithm to move by a very small amount. It's going to involve very minor joint angle changes, and then just step right through the different series. So if we're moving from one location to another that is, say, a centimeter or 2 centimeters apart, how long will it really take to go through that CCD algorithm? Hopefully not long at all, right? In fact, given the small displacement, then we can change our step resolution very significantly. We can say, okay, well, adjust each of these joints by by 0.5 degrees or 0.01 degrees or whatever else the case might be. And since we're moving such a short distance, it's going to involve a very, very small time to recalculate that position for the new set of joint parameters. Okay. So with that then, like I was saying, this afternoon I'll go through and read the, or watch those 2 videos, make sure that they're appropriate, and, don't demonstrate, the effects of killer robots on society. It's okay to discuss the effects, but can't demonstrate the effects. So I'll do that, and as long as they're appropriate for the class, then we'll go through and I'll get them posted with the refined task at hand for you guys to work on. So make sure that you get your assignment turned in to me by tomorrow morning. That's, what is this, 4? Assignment number 4. And the rest of the hour is yours to call me over and get some help and stuff. So.